My name is Shari Rothenberger. I'm a group leader in the laboratory for Earth observation in University of Valencia. I've been working already since my PhD, so more than 10 years ago, before Flex was accepted. And we were already then looking to mostly leaf level changes in the absorption and in fluorescence emission. And now we have a small group at the lab working further on this topic. So with this talk, I would like to introduce you a bit to this methodology. We are focusing on spectral unmixing strategies to understand better what's happening in the absorption and in the emission of light by vegetation. So in this talk, I will first give a background and an overview of who we are, and then on the topic of our ERC project, which is the main project we are working on now, which is related to the refinement of the FA-PAR product and improved spectral fitting strategies, and the product that will come out of that and will hopefully further come out of that, which are the fluorescence quantum efficiency, and then products that are involving the regulated heat dissipation. I will talk about how we came to this algorithm development and how we are currently validating and testing it, and so far on what would have to be further improved, and of course with some take-home messages. So the Laboratory for Earth Observation is already about 20 years and involved in some preparatory activities for the FLEX mission. We are involved both in instrumental design and operation, but also in the group we have the end-to-end scene generator being developed for the FLEX mission, which is able to simulate these complex scenes, including taking into account different atmospheres, also the whole at sensor level, what can be the possible noises and artifacts, to be able to test new protocols. Then further, we are also involved in a national level in Calval strategies for Flex, and related to also this work here, also in algorithm development for the retrieval. So there was a IFLD developed for retrieving fluorescence, and further processing chain development of the different steps to process the data. We are working on an ERC project. We are working also mostly on this retrieval algorithm, but we are focused very specifically on the reflectance signal and therefore on the changes in absorption that we are trying to mechanistically link to what's happening in the light reactions and the energy partitioning that is taking place to understand which light is being absorbed for photosynthesis and which light is not being absorbed for photosynthesis. Which strategy we are generally using for that? We are using a bottom-up strategy, which is based on looking for unique signals that are underlying the changes into the absorption. So we are designing experiments for that to be able to implement these products from a first physical bottom-up strategy. This is a bit in contrast to downscaling strategies where you have maybe being models and lookup tables being built up, and you go basically back through retrieval from different kind of set of simulated data, of model data also, which can have also a bit more the problem of ill posedness in this case. And in the case, what we are trying to basically avoid is that you have from the unique signals, you can build up like a unique spectrum. So what is the main goal? To focus a bit what we are having now unique with the Fluoris sensor on board Flex is that suddenly we have now a whole hyperspectral imaging spectroscopy from 500 to about 800 nanometers available nearly in the coming year, in the coming future. And this gives us a lot of opportunities to improve the refinement of the FA-PAR product. The FA-PAR product is just a very key global product for the current estimation of global primary productivity for GPP. And it's one of the essential climate variables that is characterizing how plants are absorbing energy on the planet. It's a scalar value at the moment. So FA-PAR, everyone understands FA-PAR as a number which is just a fraction of the total absorbed energy that is happening in the PAR region, the photosynthetic active radiation region. But the objective here is to go to a better refinement and to understand in this FA-PAR, which fractions are really going to the harvesting of this energy, which one to photoprotection, and which even inside the plants also can be pigments that are absorbing non-photosynthetic energy. The main goal here of this project is that we want to understand better how photosynthesis is downregulated, and this is by understanding and retrieving this dynamic absorption and emission properties. So here the imaging spectroscopy and the Fluoris low-resolution sensor is key to be able to resolve FA-PAR fractions of vegetations being harvested or not. And here our main goal is to detect the alternative sinks that energy is being dissipated to, which often is referred to as NPQ, being the non-photochemical energy dissipation. On the right, you see a figure that basically showing a very rough processing scheme. On top, basically, we are looking to the instantaneous product that we're after. So my goal is only to go to this step from once we have the true reflectance and the spectrally resolved fluorescence emission, to be able to develop further products that go into the further understanding of the instantaneous photosynthesis. So to be able to develop products really related to GPP, for that, of course, instantaneous photosynthesis, we need more information or more dynamical models to be able to assimilate photosynthesis on a more longer time scale, of course. So what is the challenge? In general, we have a really strong overlap of the pigments absorptions in the bar region, especially between 400 and 500 nanometers. But beyond 500 nanometers, there's less spectral overlap, and this is also where the low resolution center is going to measure. And what is another further challenge that, we have less spectral overlap here, but the signals we are looking at are very, very subtle in the absorbance and are basically only from a couple of percent change in the reflected radiance. The xanthophyll tail of the absorbance is indicated here between 500 and 600 nanometer is very subtle, and moreover, they're still overlapping with the absorption of the anthocyanins. Moreover, the other challenge is that NPQ, or non-photochemical quenching, is a very complex mechanism that has different aspects that also needs to be disentangled. So this is part of the challenge, but we like a challenge, of course. And what we need for that is we need very good spectroradiometers, because we're looking to very subtle signals. And we also need to basically design very well our protocols or experiments to be able to retrieve the signals that we are looking after. So this is already like kind of a big of jump to one of the products, but I already want to kind of introduce one of the products we after. So of course, from the spectrum, it's a bit easier to define the absorbance of chlorophyll rather than only the xanthophyll. So this is basically a definition of how we define the fluorescence quantum efficiency, where the intent is to improve the Fa par chlorophyll product to be able to calculate the A par chlorophyll A. And the fluorescence quantum efficiency is then further calculated as the fluorescence emission, total amount of photons emitted, divided by the total amount of photons absorbed. But another challenge that comes with this, and that most plant physiologists are aware of, once you plot, for example, from active fluorescence measurements, if you plot the fluorescence yield with the yield for photosynthesis, this is a very nonlinear behavior, and you have different slopes along the process. So you have a negative slope when you have high photochemical efficiency, 0.7, 0.8 you find here. But then once NPQ is activated, you have the slope becoming positive. Eventually, when NPQ saturates, you have, again, the negative slope between fluorescence efficiency and photochemical efficiency. So when you are able to measure light curves in the lab, you can easily plot this, and you come to this conclusion that fluorescence yield is certainly not enough to resolve the puzzle of the energy partitioning. So we need these additional products related to NPQ. And there comes the challenging part. So we have NPQ is still not completely fully understood molecularly speaking, but we of course know it's a process that is doing safely dissipating of excitation energy that arrives in excess to the plant. However, when this is interpreted by quenching of chlorophyll fluorescence and not generally of excitation energy, we have to be a little bit more careful. So you have the classical NPQ parameter, which contains, in fact, a mix of processes. So the main processes that we are also interested in, which is this QE process of NPQ, which involves a regulated heat energy dissipation. However, there's other kind of Q factors in this NPQ parameter, which are not really part of the genuine quenching process. For example, like chloroplast movement. Once your chloroplasts move, your absorption will lower, and therefore you will have also a lower emission in fluorescence. So this can affect also your NPQ parameter, and therefore it's also a bit difficult to disentangle all the different processes from the NPQ parameter. However, the dominant one being this QE. And additionally, to be said that there's also other processes in the quenching that will not necessarily lead to the fluorescence quenching. So what is the rationale here that we want to apply in the spectral fitting is that we are able to, step by step, try to resolve all the different spectral responses to these individual processes. So for that, we are trying to design protocols in the lab to see when certain aspects are being measured and others are contaminating the signal or not. For example, chloroplast movement is quite easy also when you look to transit in the lab, it's easy to see. You get a lot of absorption or changement over the full bar region when the shape of the whole absorption spectrum, then you know that basically this is not a single mechanism, this is basically the whole antenna that is more or less absorbing light in all the wavelengths. So the idea is, of course, to spectrally decouple all these different mechanisms. And how we do that in the lab, we started years ago to do that at leaf level. So looking to very precise changes during light transients, when a leaf goes from a dark to sudden light state, in a fast time, you go from an unquenched situation to a quenched situation, meaning that the antenna is able to dissipate the energy very efficiently in a short amount of minutes. So, and what happens then? This is the several processes that we see that are happening in this short time of couple of minutes. In the first couple of minutes, what everyone kind of normally measures through the PRI index is that you get an increase in the absorbance met with a peak around 530 something nanometers. And this is following a very quick sigmoid curve. However, what we could also distinguish is that when you wait a bit longer, so there's a time scale of 10 minutes, looking at the very fast temporal resolution of the changes in the absorbance, then you see here that there's a broadening of the first mechanism. So you have a broader peak around 550 nanometers. But also in the red edge, you see a peak at 750 nanometer where light is being increased. When you follow this also in this, the kinetic of that, it shows that this has very kind of a sigmoid curve, which indicates also that we have some kind of protein structure change in the antenna, because basically all the pigments are embedded in a protein dynamic. And when enzymes are binding to it and when there's a structural change happening, this follows a certain kind of kinetic that triggers more and more change along the process, along the speed when enzymes are binding to it to make a change in the really conformational state of the antenna. So we're looking to very distinctive mechanisms here. We can see an increase in absorption that leaves us think, okay, makes us think, okay, there's perhaps also a chemical change, but also a change in energy absorption. And moreover, there seems to be also kind of a structural change in the antenna due to the kinetic dynamic that this change is following. What I said before was at leaf level. Now I'm showing you quickly that we have seen this also at canopy scale. So here we have a system where we apply also both PAM imaging and veneer imaging at the same time during kind of a short, let's say, phenotyping unit where we can scan the canopies. And as you see here, different kind of quantum yield states during different kind of PAR conditions. So this is only the effect of increasing PAR. So there's no additional stress here. This is what would healthy plants do on a daily basis, is that when there's a bit of light coming, so here the first step would be around 300 PAR, and the last step here we have quantum yield at 1100 PAR. We have a decrease from darkness from 0.84 in the quantum yield to 0.64 at full illumination conditions. When you adapt very slowly in a diurnal scheme, which is important because compared to transients, this changed the mechanism quite considerably. What we see here that even when we apply the first step, this is delta reflectance in the change between the dark reflectance and the dark adapted reflectance. And at 300, we see again this basically the PRI peak here, and we see this peak in the red edge. These are fine peaks, so this is not following the full absorption scheme of the whole pigment bed, are really fine peaks which indicate that there's something very specific happening at molecular level. We also saw in the same setup that when you add drought stress, so when you have healthy plants, we see this two peaks here, the typical, the green and then the far red. When you add further stress, and you get basically a broadening of these two peaks, both in the green and the far red. Okay, now how we want to model that and how we want to find a model that is able to get these features out of the canopy reflectance. So we started with that a couple of years ago already, but focusing on the PRI region because this change is very easy to measure. It happens always, while the slow changes seen both at leaf and canopy level, we don't always see that easily. And moreover, the longer time you wait, there's more processes happening that spectrally can interfere. So the easy part so far has been focusing on a Gaussian model to be able to describe the peak that we see in the PRI to model it. And we found that we need 3 Gaussians to be able to describe this properly. You see that in the upper part where you see a random fitting, while in the below part we follow a more constrained fitting where we fix basically the mean and the width of the Gaussian, and we let amplitude the only parameter that can vary. What is the meaning behind this? Does it have any kind of further physical meaning behind? Well, for that we tried to, after we find the constant mean and standard deviation, we follow this along during the transient. And what we saw is that when we look to the amplitudes over time, you plot them as weight over time, you get this kind of scheme. So you have the main peak being developed definitely as a larger peak overall. But when you normalize these over each other, you see that there's some other kind of interesting dynamic that comes out. At the same time, we were analyzing the xanthophyll pigments at a very high temporal resolution. during this transients. And we see that also here, we see at a very short scale of a couple of seconds to 30 seconds, we get conversions happening in the xanthophyll pool. So here we could make a kind of a first idea about that these Gaussians are truly underlying some more molecular behavior in this PRI region. So building basically having a Gaussian peak model for this PRI observed changes with the underlying chemical behavior. It's a bit more complex than that, I have to say, but this would be like a first approach to say that these peaks are truly linked to the absorption behavior of xanthophylls. So we came to this, what you see here below. This is the one that we developed, this in the PRI region. And then we wanted to build, of course, this together with the main pigments that are from literature, although a bit modified. The absorption coefficients here you see from chlorophyll A, chlorophyll B, and beta carotenes. And we built up basically a kind of whole set of models based on the different Gaussians that are describing the overall shape of the absorption coefficient of these pigments. This is, of course, not enough because then we will have to deal with more background contributions. And for that, we are applying this kind of exponential curves that you can see here on the right. These exponential curves, although might be improved, but basically kind of resemble or could resemble also how soil behaves or how other background shapes can behave. And another kind of background, but it's basically also subpigment. So here you have the anthocyanins, which is also kind of absorbing with a peak around 530 something. But it's a way wider peak, which is also being described in literature and taken into our model. So how is our model being built? So we build up a mixture model, which is basically an estimation of the effective absorbance as a sum of the background members and the sum of the pigment members. And each of these are described based on either their function or the absorption coefficient multiplied by an abundancy weight. In the scheme, it looks like that, where we have here the pigment end members being built up, the background end members being built up, and in the mixture model being summed together. So here below, you see this in matrix notation as X being the end members or the absorption coefficients, XB from pigments and background. And B here is a vector, which is basically transpose for the abundancy factors that we are looking for. When we are measuring absorbance or either reflectance, absorbance in the lab at leaf level, but surface reflectance, we are currently making quite a very simplistic estimation of how absorbance is defined based on reflectance, which is a logarithmic conversion, as 1 minus logarithmic of 1 minus the absorbance. And this is basically our measured, let's say, a measured effect absorbance, which we, in our minimization function, we try to get the abundancy weight by minimizing the root square errors between our model sum of pigments and soil factors, absorption factors, and our measured absorbance. So the result from that, what we obtain are the abundancy weights, and we obtain that. So the fitting was applied. We apply this only for the flow rate range, because here in the end, the sensor is not measuring, but also for real data does not make sense because we have no information here due to all the light is being absorbed. And having the abundancy factors obtained for this spectral fitting, we're able to get the full multiplication of these abundancy factors with the absorption coefficients over the full power range, obtaining the full effective absorbance over this range. Here we have implemented two types of constraining. One is able to allow the overfitting, and another case which was not allowing the overfitting to test our mechanism. In general, we just allowed to be able to compare what was happening for both of them, but eventually, of course, we stick to the non-overfitting, which makes physically more sense that you, of course, don't absorb more light than you effectively have measured. So to see a bit here as a proof of concept, we're for the first time to see kind of a validation to see when we were fitting the small bump in the PRI region, if this also was being detected when we had more pool of, here in this case, anthracycline and zeaxanthin. And effectively, this was the case. We could see that there was a meaningful fitting result to be able to fit the xanthophyll pool pigments. So one of other products that here that was, of course, performing the easier one to be able to fit, which is the chlorophyll A peak. So you see here that you can find quite good relationship with the fitting result and the pigment content. So about this result, about the fitting chlorophyll, we are pretty sure that this is performing well. So one of the products that comes further out of it, once you have combined it with the fluorescence product, is, as I mentioned before, we fit the FAPAR as of the effective absorbance of chlorophyll A as a result. When once multiplied by the incoming radiance, we obtain spectrally the APAR chlorophyll. The fluorescence photons divided by this eventually gives us this FQE product. How did we further kind of look for validation to that on a larger scale? So in the scene generator for Flex, we were generating some scenes based on a scope input, and in scope you can implement a fixed value of FQE, so you can play with that within a certain kind of range. And with this, we were generating a scene with different kind of variability in LAI, and chlorophyll content, and caloric content, etc. What we obtain as stimulated spectra from the scene are not shown here, but what is shown here is basically the effective absorbance calculated from it and the fitted effective absorbance of chlorophyll. From that, we calculate the A per chlorophyll, and here below you have the fluorescence emission. But in this case, it's assuming that we have a perfect fluorescence retrieval. So this is only developed for testing the product of the spectral fitting of the reflectance. So this is the outcome of it. This is basically input from scope, and this is what we have been retrieving through our fitting. And here on the right, you see the validation. So we have quite good results with that. Only like the below line of poorly fitted ones is due to some very low LAI values. So in this version of the code, we were not able to properly account for soil spectra, which had to be improved. Another example that we're currently doing, but I'm waiting for a further outcome, is based on the highplant scenes from an alpha field, which has been growing across a couple of days. This is in total different flights about over 10 days. So you see the increasing amount of crop being developed. And here below, you see the result of the FA par chlorophyll, which comes with its abundancy weight. This is the FQE, as I mentioned before, but this alone we will not get to photosynthesis. And in the field, or in the case also for scope, we have not really any kind of, in the forward modeling, a parameter to test the amount of xanthophylls that are there. So for that, we still rely on some experiments in the lab where we are able to truly measure the content of the xanthophyll pool. And this is a last example I would like to show, which is a stress experiment on tomato plants. And we were applying both nitrogen deficiency stress and drought stress to them for along about 7 days. And then we applied a recovery period again of 7 days. So what we did here is we measured on leaf spectra both the FQE and the fitting result for the xanthophyll absorption peak. And what you can see here is what I showed in the beginning. So these are light curves showing the relationship between fluorescence yield and photochemical yield, and indicating again that, okay, with only fluorescence yield, you don't have enough. And here is a bit an example. So here you see how we combine it. So you have as a background, basically the light curve from the active fluorescence PAM measurement. And here the dots, 1, 2, 3, are on day 7, are the fluorescence quantum yield measured from the spectral fitting. So what you can see here, after 7 days of stress, you have basically the same FQE for N-deficient and control plants, but you have a very distinctive photochemical yield. So the one in control is still having a 0.5, while the nutrient deficient is about a 0.3 yield for photosynthesis. We cannot distinguish this based on FQE, but when you look to the spectral fitting results, then you see that in the control plants, we could not fit the bump of the xanthophylls, while in the case of nitrogen deficiency, we could. The other example here, where we have both nitrogen deficiency and drought leaves having a photochemical efficiency of only 0.3, we see that there's a very distinctive change in FQE. Basically, the hypothesis is, of course, that the drought leaves don't have so much capacity to develop NPQ, and they have emitted or basically released their excessive amount of energy as fluorescence. And when you see indeed to the result of the fitting of the 535 peak, you see indeed that there's a lower peak indicating lower NPQ capacity in the drought leaf. How this further can be validated to the effective pool is you can see here below. So these are the results at the same day, all the pigments being fitted, chlorophyll A, chlorophyll B, etc. And here again for the same day, control, drought, and nitrogen deficiency for the xanth peak. Here you see on the right how the xanthophyll pool normalized by chlorophyll A, because it's very important to normalize chlorophyll A to indicate what is the capacity in the antenna to have basically this photoprotective pool over the amount of antenna that there is. Then you see indeed that this is also following the same pattern. So you have a higher NPQ capacity or xanthophyll pool capacity in the nitrogen deficient leaf. So I come to the final conclusions a bit and take-home messages based on these works. So I tried to explain a bit more how FQE is not sufficient to diagnose the early stress, and that we need new products that are able to quantify regulated heat dissipation. For that, originally, we built a couple of years ago this Gaussian-based absorption model just for the PRI peak that has some underlying meaning in terms of true xanthophyll behavior. And we added that to the main absorption coefficients of chlorophyll A, chlorophyll B, etc., to be able to diversify the FA part product and be able to distinguish the energy going to either absorption or energy dissipation. At the moment, we were testing this for low resolution scenes, but this allows only for the moment a validation of FQE. But also in the lab, we were able to complement FQE with this NPQ-related xanabsorption and to validate it with pigment pool that is available and NPQ values that are available in the lab. Final conclusion is that presenting here a kind of a spectral fitting strategy that is mostly experimentally based on dynamic features that we measure in the lab. And the approach here is that we are diversifying the FAPAR product, but we are also doing this consistently in the retrieval. So all the pigments, or basically all the products, are developed in one fitting scheme. And this stands a bit in contrast with when you use different statistical or machine learning models for different traits that, of course, are not consistently connected to each other. And a spectral fitting strategy is like a main algorithm now, but of course, we are only having currently a part of the dynamics implemented. And moreover, to be able to apply this to nature and to further spectral complexity, we need to make sure that this is robust enough to be able to deal with diversity of source spectra or other type of background absorption mechanisms. So here is this one final slide on the literature that was presented. And with this, I want to further thank the funding of these projects, which is mainly by the ERC, but also part of the code was developed under funding of ESAM during the level 2 project.